Hello, hi everyone. Welcome to this online video classes. This is Dr. U. Raghavendra, Assistant Professor of Chemistry, MVS Government Degree and PG College, Mahabub Nagar, Telangana. Today in this video, I would like to explain about part 1 of coordination compounds. Okay, fine. Next. In this video, I would like to explain about the introduction of coordination compounds, about the differences in between the double salts and coordination compounds, and also I would like to explain about the importance of coordination compounds and also about the terminology which is used in coordination chemistry. Okay, fine. Next. First one is introduction. Here, generally, the in coordination compounds are generally inorganic compounds. They are inorganic compounds based on the hydrolysis property. Based on hydrolysis property, inorganic compounds generally classified into two types. They may be simple compounds or they may be complex compounds. In the case of simple compounds, the compounds they easily undergo hydrolysis to form corresponding individual ions. That is, in the case of simple compounds, the compounds undergo complete hydrolysis to form their corresponding individual ions. For example, they may be binary salts or they may be double salts. In the case of binary salt, they may be maybe like sodium chloride, magnesium chloride, or aluminum chloride. On hydrolysis, they easily forms. In the case of sodium chloride, it is sodium and chloride ions. In the case of magnesium chloride, it is magnesium and 2 chloride ions. In the case of aluminum chloride, it is aluminum plus 3 and 3Cl minus ions. In the case of double salts, for example, in the case of carnallite, that is KCl, MgCl to 6H2O, it is a double salt. On hydrolysis, this double salt produces potassium, magnesium ions as well as chloride ions. The other double salt is Morse salt. It is ferrous ammonium sulfate, that is FeSO4 ammonium sulfate 6H2. It is also undergo complete ionization on addition of water to form corresponding iron, ammonia and sulfate ions. That is, simple compounds are nothing but the compounds which undergo complete hydrolysis to form their individual ions. Okay, next one is complex compounds. Complex compounds are nothing but the compounds which undergo partial hydrolysis or which don't undergo complete hydrolysis, generally known as complex compound. Okay, fine. Next. In the case of hydrolysis of complex compound, it undergo partial hydrolysis to form complex ions. Here the complex ions, if you observe the bonds, chemical bonds present in the complex ion, generally the bonds are generally coordinate covalent bonds. That is, the bonds in the complex ion in between the central atom and the ligands are coordinate covalent bonds. So, based on this bond nature, according to modern terminology, the complex ions considered as coordinate ions and the corresponding compounds considered as coordination compounds. So, due to the presence of coordinate bonds in the complex ion, they called as coordinate ions and the corresponding compounds known as coordination compounds. Okay, fine. Here, generally, in majority cases, the complex compound or coordination compound generally very important in the case of transition elements because all the transition elements, majorly most of the transition elements forms various coordination compounds. Though it is applicable to transition elements chemistry, there are some main group elements as well as some inner transition elements, that is a block elements forms coordination compounds. In the case of main group elements, they may be aluminum, or maybe tin or maybe lead. There are some example which can also form coordination compounds just like as transition elements. Okay, if you observe the example for coordination compounds, they may be potassium hexacyanoferrate, or it may be hexamine cobalt chloride, or it may be diamine silver chloride, or it may be tetracarbonyl nickel, or it may be lithium tetrahydroaluminate. Here, the simple salts, that is double salts, mainly double salts and coordination compounds. Double salts and coordination compounds both are obtained by the combination of two stable compounds, that is double salts and coordination compounds both are obtained by the combination of two stable compounds or molecules in stoichiometric ratio. Okay, but they differ in their hydrolysis property. So there are some differences in between the double salt and coordination compounds, though they are obtained from the two stable compounds. Okay, fine. Next, what are the differences in between the double salt and coordination compounds? Here it is double salt, here it is coordination compound. The first one is generally double salts are obtained by the combination of two different salts, but the case of coordination compounds, they are obtained due to the interaction of ligands with central metal atom or ion. The next one is in the case of double salts, they don't have any coordinate covalent bonds in their structure. They have only ionic bonds. But in the case of coordination compounds mainly contain coordinate bonds in their structures. Next, in the case of double salts are stable only in solid state. On addition of water, they undergo hydrolysis, thereby they lose their identity. But in the case of coordination compounds, they are stable even in their aqueous solution. They don't undergo complete hydrolysis, so they don't lose their identity. That is, coordination compounds retain their identity. Double salts generally form simple ions on hydrolysis, but in the case of coordination compounds, they form complex ions on hydrolysis. In the case of double salts, it is easy to analyze the double salts based on the analysis of their individual ions. But in the case of complex compounds, it is difficult to analyze the compounds based on their individual ions, that is based on the complex ions. In the case of double salts, generally metals atoms or metal ions shows normal valency, but the case of coordination compounds, during the formation of coordination compounds, the metal atom or metal ion may shows abnormal valencies. In the case of double salts, there are some example for double salts. They may be carnallite, they may be more salt, or they may be potash alum. For coordination compounds, they may be potassium percyanide or they may be hexaamine cobalt chloride. There are so many coordination compounds. Okay, fine. Next, importance of coordination compounds. In order to know or in order to study the coordination compounds, we have to know the importance of those compounds. It is essential to know the something about the coordination compounds because they have lot of application in our day-to-day life. Generally, coordination compounds are well known since the beginning of modern chemistry, even though they also known in the early stages, such as the dyes, for example, Prussian blue. Here, the Prussian blue is the first coordination compound, which is well known to the mankind. That is here the Prussian blue is nothing but it is the peric ferrocyanide which contains deep blue color. Okay, here generally coordination compound generally play a vital role in many fields. They may be in analytical chemistry, metallurgy, biological system, industry, as well as medicine. If you observe the importance of coordination chemistry one by one, if you observe the importance in analytical chemistry, coordination chemistry or coordination compounds are very essential in analytical chemistry. Here analytical chemistry generally it is two types, may be qualitative analysis or it may be quantitative. Generally it is used to analyze the inorganic salts or in order to find out the inorganic ions. In the case of qualitative analysis, we should find out the specific ions in the given salt mixture. In the case of quantitative analysis, we have to find out the quantity of that particular ions. Okay, if you observe the importance with some examples, here the cupric ions generally detected by the addition of ammonia. If you add ammonia to the cupric solution, then we get deep blue color solution. It is due to the formation of copper amine complex compound. It is generally tetraamine copper compound, copper complex compound. So we get deep blue color. If you get deep blue color on addition of ammonia to the cupric solution, then we can confirm this salt solution contain cupric ions. The other one is we can estimate or determine the nickel plus 2 ions by the addition of DMG, that is dimethyl glyoxymeto. It is a complexating agent, that is it can easily form complex compounds with the specific metal ions. Mainly it is forms complex compound with nickel plus 2 ion. On addition of DMG to the nickel plus 2 ion solution, then it converted into bis dimethyl glyoxymeto nickel complex, which is generally a scarlet red PPT. Based on this PPT, that is based on the amount of 50 obtained in the reaction, we can estimate the nickel plus 2 present in a given salt mixture or salt solution. Okay, here the hardness of the water can also be estimated by using EDTA as a complexating agent. Here generally water is two types, one is soft water and second one is hard water. Soft water generally based on this classification is generally based on the reaction with detergent. If the water easily forms foam with the detergent, it is known as soft water. Generally soft water contains sodium minerals. If the water don't form foam easily with detergent, it is considered as hard water. Hard water generally contains calcium, magnesium minerals, that is they are mainly calcium, magnesium chlorides, sulfates and carbonates. Here the hard water, that is the estimate, we can estimate the hard water, that is estimation of calcium or magnesium ions in the hard water can be done by using EDTA. If you add EDTA to the hard water, then the EDTA undergo complexation with calcium and magnesium ions and converted corresponding magnesium and calcium EDTA compounds. Based on their EDTA, magnesium and calcium EDTA compounds, we can estimate the amount of calcium or magnesium ions present in hard water. Okay, next, importance in biological systems. Coordination compounds have great role or they play great role in biological systems also. For example, chlorophyll, hemoglobin, chlorophyll and hemoglobin as well as so many enzymes are essential for biological processes. Here the chlorophyll generally present in green plants. It is a green pigment. It is nothing but here the chlorophyll is nothing but it is a magnesium plus 2 ion coordination compound. It is essential for photosynthesis. Without chlorophyll there is no photosynthesis reaction. Due to the photosynthesis reactions, plants produces carbohydrates which are essential for the survival of all living beings on the earth. So if there is no photosynthesis reaction, there is no survival of life on the earth. So photosynthesis alternately depends on the presence of chlorophyll. Here chlorophyll is one type of coordination compound. So it is essential, that is coordination compounds are essential for the survival of life on the earth indirectly. Here hemoglobin. Hemoglobin generally it is a coordination compound of iron plus 2, Fe plus 2. Generally it present in blood. It is a red pigment of blood. Generally it present in RBC, red blood cells. It is essential for transportation of oxygen and carbon dioxide. That is, it transport oxygen from the lungs to the body parts and removes or take back the carbon dioxide from all the parts of the body to the lungs. So it is essential, that is hemoglobin is essential for the respiration of animals or living beings. So the iron coordination compound, which is nothing but hemoglobin, is essential for biological processes. Here there are also some enzymes such as carboxypeptidase, alcohol dehydrogenase, or carbonic anhydrase, or kidney phosphatase, urease. There are so many enzymes. Here the enzymes are generally they are metalloproteins, where the one or more than one amino part of the proteins are bonded to or coordinated with metal ions. That is, these are metalloproteins. Generally they contain some color, so they are also known as chromoproteins. These chromoproteins or metalloproteins are they are acts as enzymes in so many biological processes. Without enzymes there is no functioning of some biological processes in the body. So it is essential that the importance of coordination compounds in sustenance of living beings. Okay, fine. Next, here the first and second, these two are metallophosphorins. Here it is iron phosphorine, it is magnesium phosphorine rings. Phosphorine rings are nothing but they are tetraferrol systems, which are in which the four ferrol rings are connected through CH2, that is methylene groups. Here the first one is hemoglobin structure, the second one is chlorophyll structure. These two are generally coordination compounds. Here the yellow one is it is the reaction for estimation of nickel by using DMG. If you add DMG to the nickel plus 2, we get the red color or red scarlet red color nickel DMG complex. Based on this complex, we can estimate the nickel plus 2 ion. Here the first and second are these two are the complex compounds or coordination compounds of magnesium and calcium with EDTA ligand. EDTA is nothing but is a complexating agent, which is nothing but ethylene diamine tetraacetic acid. Here the EDTA undergo reaction with in tetraanion form, that is in the form of tetraacetate. Then only it acts as hexadentate, that is ethylene diamine tetraacetate acts as hexadentate. Okay, fine. Next, one, importance of coordination compounds in metallurgy. Generally metallurgy deals with the extraction and purification of metals from their ores. Here during this metallurgical process, coordination compounds plays they play important role. If you observe some example, Generally, the noble metals such as copper, iron, and silver generally extracted and purified by using coordination compounds process. Here in this extraction, a noble metal extraction process, the noble metals generally, the first step treated reacted with cyanide ligand, then they converted into corresponding cyanide complex compounds. This cyanide complex compound on degradation produces pure metal. Similarly, here nickel metal also prepared or purified by using Mond process. Here the nickel ore in the first step treated with carbon monoxide, that is CO, like God, carbon monoxide, then it converted into tetracarbonyl nickel complex compound. This complex compound on heating at higher temperature converted into pure nickel metal. So by using this Mons process we can prepare the or as well as purify the nickel metal. These are example for importance of coordination chemistry or coordination compounds in the metallurgy. Next one, importance in medicine. Coordination compounds or coordination chemistry also plays major role in medicine field. Here, for example, the cisplatin. Cisplatin is nothing but it is a coordination compound of platinum. It is nothing but cis diamino dichloroplatinum complex. It is generally used for the treatment of cancer as well as some other complex compound are also used for the treatment of different diseases. Generally, it is coordination compounds or coordination chemistry is important. It plays or it play greater role in chelating therapy. Chelating therapy is nothing but it is the treatment of some specific diseases by using chelating agents. Here, the chelating agents are nothing but the ligands which can easily form or ring-like structure around on the specific metal ion. Here, the lead poisoning. Generally, heavy metals are very poisonous metals. So, the lead poisoning generally treated with EDTA chelating agent as well as arsenic poison is generally treated with ball, that is British anti-levisite, that is EDTA is for lead poisoning, ball is for arsenic poisoning. Okay, here next in industry. In industry also coordination compounds play a great role. Generally, many chemical reactions occur at drastic conditions, that is high temperature and high pressure uh, values. If you use some catalyst, the reaction takes place under mild conditions. Here also by using some coordination compounds as catalysts, we can carry out the reaction at normal conditions, reaction conditions. So if you observe some example, Wilkinson catalyst generally used for the hydrogen of alkenes. The other one is Ziegler-Natta catalyst, which is used for polymerization of alkenes. Okay, let us see about this this coordination compounds in the next slide. Next, here the first one is it is the complex compound found in between the lead and EDTA ligand. Generally, the lead poison patient gives the patient which is poisoned by lead metal. Generally, he given EDTA tablets. Here, the EDTA undergo reaction with lead to form this type of complex, which is usually extracted or removed through urine. Here, the arsenic poisoning is treated with ball, British anti-Lewisite. That is, ball is an antidote for arsenic poisoning. Here ball is nothing but it is alcohol derivative or hydroxy compound. Here it is propanol derivative. Ball is propanol derivative. Generally ball is nothing but 1 2 3 2 3 dimercaptopropanol, 2 3 dimercapto 1 propanol. It is nothing but British anti-Lewisite. It is used as a antidote for Lewisite. Lewisite is generally arsenic complex compound which is poisonous to our body. So it is removed by adding ball as the antidote. Okay. Here Lewisite is first used in World War I by Britishers. Okay, next, Ziegler-Natta catalyst. Here Ziegler-Natta catalyst is produced by the combination of titanium tetrachloride and triethyl aluminum. This is Ziegler-Natta catalyst. In the presence of Ziegler-Natta catalyst, alkenes undergo polymerization to form polymers. Polymers have a lot of application in polymer industry. Okay. Next, it is Wilkinson catalyst, which is nothing but triphenyl phosphine rhodium chloride. Triphenyl phosphine rhodium chloride used for hydrogenation of alkenes. Next, terminology used in coordination chemistry. The first one is coordination entity. Generally, it is coordination entity constitutes a central metal atom or ion which is bonded to a fixed number of molecules or ions, which are nothing but ligands. That is, coordination entity constitutes the central atom or ion along with the ligands which are bonded to the central atom or ion. For example, nickel tetracarbonyl or hexaamine cobalt ion. These are coordination entities. Next, central atom or ion. Central atom or ion is nothing but it is the atom or ion which present in the coordination entity and directly bonded to the ligands. That is, the atom or ion in the coordination entity which is directly connected or bonded to the ligands, generally known as central atom or ion. Here in the nickel tetracarbonyl and in cobalt complex, the central atom or ions are generally they are nickel and cobalt plus 3 ions respectively. Next, ligands. Ligands are nothing but these are the ions or molecules which are directly bonded or connected to the central atom or ion through coordinate bonds. That is, the molecules or ions which are bonded to the central atom or ion through coordinate bonds, generally known as ligands. Generally, ligands are connected to the central atom through donor atom. Generally, donor atom contains at least one lone pair of electrons. Generally, coordination compound formed due to the combination of two species. One is central atom, second one is ligands. Here, in order to form a complex compound or coordination compound in between the central atom and ligand, there are two conditions. One is central atom must contain vacant d orbitals, as well as the second one is the ligands must contain at least one donor atoms, or they must contain lone pair of electrons on donor atoms. Okay, these are the conditions to form coordination compound in between the central atom and the ligands. Okay, Ligands may be simple ions. They may be simple ions such as hydride, chloride, hydroxide, nitrite. They may be simple molecules like water, aqua, amine, or they may be some large molecules such as ethylene diamine or EDTA. Or in some cases, they may be macromolecules like proteins. Okay, fine. Next. Generally, ligands classified into different types based on the nature of donor atom as well as number of donor atoms. It is mainly based on the denticity of ligands. Here the term denticity is nothing but it is the number of donor atoms of ligands which directly connected to the central atom or ion in the complex compound known as denticity of that particular ligand. Density generally equal to number of donor atom present in the ligand. So based on the donor atom or based on the density, ligand classified into different types. They may be monodentates, which are called as unidentates. Monodentates are nothing but the ligands which contains only one donor atom, generally known as monodentate. For example, water molecule, aqua molecule, amine molecule, or chloride, cyanide, nitrite, anyone. Okay. Next, bidentates or bidentate ligands. The ligands which have two donor atoms, generally known as bidentate ligands. That is, the denticity of bidentates is 2 because they have two donor atoms. For example, oxalate, carbonate, ethylene diamine, so on. Polydentates. Polydentates are nothing but the ligands which have more than two donor atoms. That is, the denticity is more than 2. Denticity is 1. That is, they have one donor atom, that is monodentate. Denticity is 2. That is, they have two donor atom. They are known as bidentates. If denticity is more than 2, they may be tri or tetra or whatever it may be. That is, they are example for polydentate ligand. For example, diethylene triamine, it is tridentate. Here EDTA -4, or it is nothing but ethylene diamine tetraacetate. It is example for exodentate ligand. Diethylene triamine it is example for tridentate. Okay, fine. Next, if you observe the example for various types of ligands, the case of unidentate, they may be water molecule, ammonia, fluoride, chloride, cyanide, thiocyanate, hydroxide, or nitrite ion. In the case of bidentate ligand, it may be ethylene diamine, it may be oxalate ion. In the case of polydentate, it may be diethylene triamine or triphosphate ion or ethylene diamine tetraacetate. The other example, that is mainly the amine ligands. In the case of amine ligands, the first one is monodentate ligands. Monodentate ligands contains only one donor atom. In the case of amines, nitrogen contains one lone pair of electrons, so it acts as donor atom. So in the case of monodentate amine ligands, the amines must contain one donor atom. So examples are, it may be ammonia or it may be amines. That is, it may be primary amine or it may be secondary amine or it may be tertiary amine which contains only one nitrogen atom, or it may be pyridine. In the case of bidentate ligands, they may be ethylene diamine or methyl ethylene diamine or 1,3 propylene diamine, or it may be glycine. Here glycine is one type of amino acid, alpha amino acid. Here it contains one nitrogen donor atom, one oxygen donor atom. Next, example for tridentate ligands, they may be diethylene triamine, it is known as simply diene. Example for tetradentate, example is tetradentate, example is triethylene tetraamine, triethylene tetramine, triene. Example for hexadentate ligand, it is ethylene diamine tetraacetate. Okay, fine. This is all about examples for different ligands based on their denticity. Okay, next, chelating ligands. Here the chelating ligands are nothing but the ligands which can easily form ring-like structure around the central atom or ion, generally known as chelating ligands. Generally, di and polydentates ligands act as chelating ligands because they easily forms ring-like structure with the metal ion through attachment at more than one sides. So they act as chelating ligands. Chelating ligands generally based on their denticity, as I explained in the previous slide. Denticity is nothing but it is generally resembles the number of donor atoms through which the ligand can connected to the central ion. That is the total number of donor atoms present in a ligand to which the central atom is bonded, generally known as denticity of that particular ligand. Denticity generally denoted by Greek letter K, which is nothing but kappa. Generally, we have to mention the denticity of that particular ligand as a prefix before the name of that particular ligand. In the case of EDTA, it is hexadentate, so it is denoted as K6 EDTA. Here denticity is different from the heptosity. Here in denticity generally it is the number of donor atoms of a particular ligand which are non-contagious atoms. That is, here in the case of ligand denticity, the donor atoms are non-contagious atoms. That is, they are not connected together. In the case of heptosity, the donor atoms are contagious each other. That is, they are connected each other. Okay, this is different in between the denticity and heptosity. Next, ambidentate ligands. Ambidentate ligands are the ligands, one type of ligands which have a capability to connect the central atom or ion through two different donor atoms. That is, if the ligand has a capability to connect the central atom or ion through two different donor atoms, then it is known as ambidentate ligand. For example, the best examples are nitrite ligand and thiocyanate ligands. In the case of nitrite ligand, it contains two types of donor atoms. One is nitrogen, second one is oxygen. In the case of thiocyanate ligand, ambidentate ligand, it contains two donor atoms. That is, one is sulfur atom, second is nitrogen atom. So they can connect through different donor atoms. So they are ambidentate ligands. Okay, fine. Next. Here the structure resembles the chelation or chelating ligands. Here the in the first structure, these rings are generally the compound or generally phenanthrene compound. It is a bidentate ligand. Three phenanthrene molecules forms rings around the ruthenium plus 3 ions. They are chelating ions. Here in the second structure, the nickel plus 2 connected or bonded to 2 dimethyl glyoxime ligands. Here the dimethyl glyoxime is also a bidentate ligand. They also form a ring-like structure around the nickel, so they are chelating. In the case of third structure, it is EDTS ligand, ethylene diamine tetraacetate. It is hexadentate ligand. It can easily form 6 coordinate bond with the metal. Okay, fine. Next, here it is nitrite ambidentate ligand, which can connect a metal or which can bond to the central atom through nitrogen donor atom, or it may connect through oxygen donor atom. In the case of ambidentate ligands, during the nomenclature of compound, if the compound contains ambidentate ligand, it is essential to mention the symbol of donor atom after the name of that particular ambidentate ligand. So here the if the nitrite ligand bonded through nitrogen donor atom, it is nitrito N. If it is bonded through oxygen atom, it is nitrito O. In the case of thiocyanate ambidentate ligand, if the thiocyanate is bonded through sulfur, we have to mention it as thiocyanate S. If it is bonded through N, we have to mention it as thiocyanate N, or we can simply mention as isothiocyanate. Okay, fine. Next, coordination number. Coordination number is nothing but it is the total number of metal ligand bonds present in coordination compound or coordination sphere. That is the total number of metal ligand bonds found by the donor atom of the ligands, which through the formation of the donor atom of the ligands with the central ion in a coordination sphere. That is the total number of metal ligand bonds which is formed by the donor atom of the ligands, generally known as coordination number. In the case of platinum hexachloride compound, it is coordination number is 6. In the case of hexacyano, it is simply also here also 6. Okay, next, coordination sphere. Generally here coordination number can be calculated by, here coordination number is does not equal to total number of ligands. It is coordination number is generally equal to the total number of coordinate bonds formed by the ligands with the central ion. So in the case of unidentate ligands, coordination number Cn generally equal to the total number of ligands. But in the case of polydentate ligands, coordination number generally always equal to denticity into total number of polydentate ligands. That is the case of polydentated complexes. We can calculate coordination number simply by multiplying denticity with total number of polydentate ligands. But in the case of unidentate ligands, it is simply equal to total number of unidentate ligands. Okay, here next one is coordination sphere. Coordination sphere, generally in order to name a particular compound or in order to write a coordination compound, we have to write the coordination we have to write the central metal atom or ion along with the ligands which are bounded directly to the central ion within the square bracket. So here the coordination sphere is nothing but the central atom and the ligands which are directly bonded to the central atom or ion mentioned within the square bracket, generally considered as coordination sphere. Here if you observe the example, in this compound the coordination sphere is this one. Here the remaining Cl3 or 3Cl minus are generally considered as counter ions. that is the ligands which are placed in the coordination sphere don't undergo ionization, but the ions which are present outside the coordination sphere generally undergo ionization. Those ions which undergo ionization considered as counter ions. Okay, fine. Next, coordination polyhedron. Here, in the coordination compounds, generally the donor atoms of the ligands in the coordination compounds or complex compound, the donor atoms of the ligands bonded to the central atom or ion in a particular direction in order to give a particular geometry to that compound or to that complex compound. This particular geometry generally known as coordination polyhedron. That is, in a coordination compounds, the donor atoms of the ligands generally arranged around the central atom in a particular direction which provides a particular geometry to that particular compound, generally considered as coordination polyhedron. Here, based on the coordination number, the coordination polyhedron may be different. If the coordination number is 6, then the polyhedron coordination polyhedron is octahedral geometry. If the coordination number Cn is 4, then it is tetrahedral geometry. If Cn is 4, it may be square planar. That is, in the case of 4 coordinated complexes, the polyhedron or the geometry may be tetrahedral or it may be square planar. If in the Cn, that is coordination number is 5, then the polyhedron or the geometry may be trigonal bipyramid or it may be square pyramid. Okay, based on the coordination number, the coordination polyhedron may be different for different complexes. Okay, fine. Next, here oxidation number of central atom. Here oxidation number is nothing but the charge present on the central atom or ion. If we remove all the ligands from the coordination sphere, then it is known as oxidation number of that particular central atom or ion. Okay, generally during the nomenclature of compound, here the oxidation number of central atom generally denoted by Roman numerals. During the nomenclature, it is generally mentioned within the parenthesis in Roman numerals after the name of that particular central atom or ion. If you observe the example, the case of potassium ferrocyanide, it is written as potassium hexacyanoferrate 2. Here within the parenthesis, it is the oxidation number of iron. Okay, next, homoleptic and heteroleptic complexes. Homoleptic and heteroleptic complexes. If the complex compound or coordination compound contains only one type of ligands within the coordination sphere, then it is known as homoleptic compound. If the complex compound or coordination compound contains two or more than two different ligands, or if the complex compound contains more than one different ligands within the coordination sphere, then it is known as heteroleptic compound. Homoleptic compound contains all same type of ligands within the coordination sphere, but in the case of heteroleptic, The compound contains different ligands in the coordination sphere. Okay, if you observe the example, this is example for homoleptic because all the ligands in the coordination sphere are ammonia molecules. This is example for heteroleptic because the coordination sphere it contains three amine molecule, three chloride ions, so different ligands. So it is heteroleptic. Okay, fine. Next, sorry. Thank you. Thank you very much for your patience for watching this video. Thank you one and all. Okay, bye.